two things. First of all, for those of you that are attending or presenting at CNS, which is on October 25th and October 26th, first of all, make sure that's marked on your calendars and that you're going. And second of all, start working on your presentation if you haven't already.
Yeah, and actually, to put it another way, if you do not have a presentation and or a poster or a lightning talk, and you have been working with us for more than a year, you should have one, and you should bring that up.
What about more than a year? What do you mean is more than 2 weeks?
Yeah.
So if you didn't just show up.
So if you didn't just show up, then we are hoping that everyone participates either in doing a poster or a lightning talk, and so please let us know what those will be.
Yeah, I think putting a poster together is just something that is a good skill to have in general. And yeah.
Well, also, this is also a huge, the reason we do these is so that at the banquet, that people who are visiting come and talk to you about the things that you're interested in. Because otherwise you are just a nameless, person with a face. Otherwise you were that person who went up there and said had that outrageous idea for 2 minutes. That's not that hard, and now you are an interesting person to talk to.
And does anyone have a 5-minute thing they want to present today? I didn't see anything on the slide, so I don't know.
I can rant about it.
Yeah, even a 5-minute, like, oh, I ran into this thing and I can't believe it. Results, anything?
Well, I got less than 5 minutes.
Yeah.
Every Wednesday, me and my friend have game night. We have lost 2 of our people through graduation and through international travel. We're looking for 2 more. So if you would like playing board games, let me know.
That was less than 5 minutes.
All right, so I have the distinct pleasure to have stolen Dan Williams from OSDI, which is happening just up the road. So Dan was a PhD student at Kernel, and after Kernel joined IBM, and is going to be talking to us about some pretty cool work on some pretty cutting-edge topics related to containers, virtualization, and Unikernels.
All right. Okay. Yeah, so thank you for the introduction. So I guess maybe that means my first slide isn't that important anymore. So yeah, this is me. So yeah, like you said, I've been at IBM for, well, I guess you didn't say this, but I've been at IBM for about 8 years. Mostly I've been studying things around OS and virtualization in the cloud setting, and the past few years it's been about Unikernels, which I'll explain more about. I have a couple of slides at the beginning here about IBM Research in case you haven't heard of it before. It's kind of a big organization. There's 3,000 researchers and scientists, 12 global labs, 6 continents. So this is our slogan, the world is our laboratory. And to brag a little bit, there's a lot of really nice medals that people have received. Unfortunately, I'm not on the list of recipients.
Quick question, are you recruiting interns?
Yeah, so I mean, we are always kind of interested in looking for good people for both internships and full-time positions. So
I have an honest question.
Yeah.
Could you be more specific about your lab in Africa?
What do you mean by more specific?
This
This is Africa.
It
Yeah,
exists.
it's in Nairobi. I think it's a fairly new lab. I haven't. So the ones I visited are one, which is Watson. So yeah, so this is the one that I work in, which is Yorktown Heights. It's the biggest one of all of them. It's kind of this cool 1960s building, about 35 miles north of New York City. So as you can see, it doesn't really look very city-like there. And it's a nice place because there's a lot of notable things that have happened in that building, which is kind of cool. This was the view outside my office. That's a quantum computing lab, which is kind of cool to see them, doing whatever they do in there. But I have since switched offices because the quantum computers were very noisy. Mostly it's the cooling pumps. All right, so I just want to start by kind of giving an overview of some of the things that are happening at IBM Research, and kind of like narrowing down into what I work on, just to give you a bit of a taste. So there are lots of things like the quantum group, the AI stuff. I'm not going to talk about those at all. I'm in the group that is the cloud research group. And within the cloud research group, there's the cloud platforms group. And these are the people who are mostly concerned with, the cloud platforms. So this encompasses things from microservice level. So this is like microservice meshes, things like Istio are worked on in that group. There's a bunch of work on serverless. So OpenWhisk, if you're familiar with that, came out of that group. A lot of people are working on Kubernetes, which is the container management preferred thing at IBM at the moment. And then there's also people looking at security for containers, whether that's the provenance of container images or layers or integrity measurements and this type of thing. So what you'll notice is in the cloud platforms group, there's a big focus on containers, and I think this is represents what's where the hype is in the industry at the moment. So just to make sure that we're kind of on the same page about what we mean by containers, the way that I think about them is that it's sort of the unit of computation that we think of in the cloud. There's a couple of key distinctions. So typically these are compared to virtual machines, which were the dominant unit of computation in the cloud for the past decade or so. So a virtual machine would have a guest OS inside of each guest, whereas the container is now virtualizing at the Linux kernel layer. So the interface that the guest sees from the host is either a virtual hardware abstraction in the virtual machine one, or kind of a kernel-y abstraction in the container one. So another key kind of difference or a key idea that we have about containers is that they're very much applications. We think of them as applications and less like systems. So whereas VMs, you might run multiple applications inside one. You might configure that system. You might SSH into it and fiddle around a little bit. Containers, we very much think of these as sort of single applications that you don't SSH into and fiddle around with. You do that in other ways, like this is the immutable infrastructure thing, if you guys are aware of that. The reason that containers have sort of been interesting to IBM in the cloud sense there's a lot of different reasons, and I've just listed a few over here. So one of the reasons is that the images for the containers are so much more lightweight than these virtual disks that we were dealing with virtual machines. So this gives us advantages in portability and density. For a cloud provider like IBM, we like how the containers are more easily introspectable by tools in the host. So it's very easy for us to run something that looks inside the file system of the container and check some configuration files or something like that, and gives the cloud user some kind of added value, saying oh, maybe you should upgrade that package or something like that. And the other thing that people like about containers is that some of these system administration tasks that the client would have to do in their virtual machine are now decoupled from the client's responsibility. So that means that the cloud provider gets to do that for them and add value in that way. But so that's why we like containers. But so container isolation has been sort of a target when people start talking about what the downsides of using the containers are. So when you compare these to VMs, you typically hear things like they're relatively poorly isolated. And this is kind of going to be the subject, or the subject of the rest of the talk that I'm going to give. So I'm going to go into a little bit more detail about what I'm talking about in terms of isolation and some of our approaches to apply some concepts from Unikernels to the containers to improve the isolation story. All right. Yeah.
Is there any empirical evidence that containers have had worse isolation in practice than real mass market VM?
So, so if you're talking about like studies,
Right.
so yeah, so I can tell you in terms of some anecdotal stories that I've heard. from people about specific vulnerabilities that containers have that VMs don't. In terms of
The VMs have totally gotten known.
I've totally got. Oh yes, yes. So yeah. So I think that I think maybe we should defer this a little bit later. So because the second part of the talk is going to be talking about this. But I guess the general feeling is is one of happiness with VMs, and I'm going to go into why this doesn't really make sense and how to kind of go down into it. Some of the things that were happening with containers, especially at the start when they were just starting to become popular, is very simple things like fork bombs were happening in containers and stuff like this, which was what led them to have this reputation of worse properties. Okay, so and again, like I'm going to go through some of how we try to measure the isolation in this next part. So. All right, so just to kind of get on the same page about what we're talking about when we're talking about isolation. For the purposes of this talk, we're really concerned about having a container that is trying to compromise the lower layer of software in order to affect another container on the system. So really, we're focusing in here on the software deficiencies in that lower layer. So this is really an attack surface. Software type concern we're looking at. We're making some assumptions in this work. We're going to trust hardware isolation, even if that's perhaps not the best assumption here. So we're trusting that hardware page tables do what they're supposed to, et cetera, and we're not considering covert channels or side channels or things. So we're really just on this work, we're just looking at this attack surface to the underlying software layer. So. So as I said, the virtualization has kind of been the standard in terms of isolation for the past decade or so in the cloud. And the reason for this, like when you start thinking about why virtualization has this reputation, it has to do with the level of the interface to the host. Right? This is what we think is the reason that that VMs are considered to be isolated. And so by low level here, what I'm really talking about is the level of abstraction that the host manages. So for instance, if you have a virtual machine here, the guest OS is going to implement things like the TCP IP stack. It's going to implement things like the file system. And the host is just going to implement something like a block device or a network tap device that operates on the packet level. So if you compare that to something like a container, we would say that has a higher level interface because it is directly able, it's working with these directly exposed abstractions like the sockets and the file systems. So the reason that this level of interface, so to see why the level of interface has to do with this isolation in this way, there's some amount of argumentation that goes along this line. So the lower the level of interface, typically, you'd think that could be implemented with less code. And if it was implemented with less code, you'd hope that would have fewer vulnerabilities. If it had fewer vulnerabilities, you'd hope that it was able to give stronger isolation. And I understand this is a bit of a hand-wavy sort of thing, but this is what I believe that people. This is what I believe is behind the feeling about VMs being more isolated. So what we really wanted when we were starting this work is we really wanted a way to measure how these interfaces affected the isolation. And the one that so the metric that we ended up using is trying to measure the amount of accessible code as a proxy for that isolation. And so to do this, we used the Linux ftrace tool to see all of the kernel functions that are accessible through an interface. So I want to point out that this metric is not a great metric. There are certain things that are misleading about the metric, which we can talk about later. But I think the reason that we think it still has some value is I think it captures this intuition behind this level of interface and why that relates to isolation. So to see the metric kind of in action, we have we've run a little experiment using the ftrace, and for this experiment we have a very simple web server, and we ran that both as a virtual machine as well as a process, and we measured the amount of kernel functions that it was using. So there's a couple of things to notice here. Oh, so we classified the functions depending on what part of the system we manually classified. And so there's a couple of things to notice. The first one is that this networking piece has shrunk. If you run it in a virtual machine, the networking piece shrunk. You need less networking kernel functions, and this makes perfect sense, right? This is the whole thing about who is implementing the TCP stack. The TCP stack, in this case, is implemented by the kernel, so that counts under the host. And in this case, it's implemented in the guest. The second thing that I want to point out about this is that the virtual machine does indeed shrink that bar, although it might not be as much as we might expect. And there's a couple of reasons for this. One is that the benchmark that we're using isn't using much of the kernel, so that's why we're seeing that. And then the other thing is that there's this big piece here, which we have identified as virtualization related functionality. So these are like the KVM functions and stuff that's going on in the host. So doing these like initial experiments led us to ask this question, which is, why do we really need this thing? Do the virtualization hardware or mechanisms really have anything to do with isolation? Because, like I said, our intuition is saying that this is a high-level, low-level thing, not necessarily something to do with whether or not you use VT hardware or if you're using standard page tables. So we wrote a provocatively titled paper that we sent to Hot Cloud this year. It's called "Say Goodbye to Virtualization for a Safer Cloud," which I guess gives away the conclusion that we made, or the point that we're trying to make, which is that we don't think the interface level actually is really tied into the fact that you're using virtualization mechanisms or not. And we think that these things are confusing the issue of isolation in the cloud. So to see that a little bit more and graphically, I guess, I have these two zones, the low-level interfaces and the high-level interfaces, and that's sort of on a spectrum. And at the top, I have these ones that use virtualization mechanisms. So like this is like a standard VM, as we said, has a low-level interface. But if you think about things like paravirtualization or even directly exposing system calls through hypercall mechanisms, and this has been done in things like Dune or more recently in gvisor in the KVM mode, you can kind of imagine that these, or you can see that these virtual machines these things that are using the virtualization mechanisms can have high-level interfaces. And similarly, you can take the process and you can start looking at that, and you can add a library OS component to it, and now it looks like it's using lower-level interfaces. So there's this kind of fluidity about changing the interface level, regardless of if you're using the VT hardware mechanisms or not. So to revisit our picture from before, this is the same graph. We've added a new bar. And this one is the same user space process, but this time it's running a user space network stack. And so we see what we would expect, which is that network thing has shrunk down. But in this case, we have this other observation, which is not only did we shrink from comparing to a process, but we've actually gotten lower in this kernel function metric than KVM. And this is indicative of us avoiding this virtualization complexity. And again, this is somewhat special to this particular application. If you had an application that was using lots of the file system, just moving the network stack wouldn't necessarily get you lower than what the VM would look at. So to pop up a level and to see how this relates to the containers that we were talking about, the container isolation problem that we're looking at, I think this is intended to motivate our approach to how to get better isolation for these containers. And the basic idea here is if you can limit the system call interface to those low-level interfaces, then you can have this level of isolation that comes with being a low-level interface. Yeah.
I'm sorry to interrupt, but when you say isolation,
Yeah.
are you worried about performance isolation Are you worried about protection? Are you worried about blast radius? What do you mean by isolation?
Yeah, so we're not performance isolation. We're mostly concerned with the ability of an attacker to be able to compromise the underlying level and read or write state or modify the execution of the other thing. So it's really kind of a protection thing. Does that?
So, even if I was running processes in an OS,
Mm-hmm.
if it's not performance
Yeah.
isolation, what kind of protection would that fail to provide that you were running with?
So what we would argue is that a process would have a very large system call interface, and this is through this the high level interface. And because it's a high level interface, we would say that you have a larger attack surface, more opportunity to compromise the lower layer. Whereas if you had a virtual machine, for example, we're arguing that a lower level interface would be less of an attack surface from which you can mount these attacks on the lower layer.
So I guess my question, what kind of attack? What are you contemplating as an attack?
Well, yeah.
So when I think about protection, I'm not worried necessarily about maliciousness. I'm just worried about, cache.
Yeah, no, yeah, so the environment, I'm sorry, I just want to be clear. The environment is that the containers that are on here are mutually distrusting, and they may actively try to attack the host. So this is like whether they try to do a buffer overflow on a system call, whether they try to do some file system exploit like a dirty cow or something like this, in order to either get more privilege on the host, so they can then start to affect what other processes are doing, read out the secrets from other processes and things like that.
So is the insight or the intuition just that if you have the same amount of security vulnerabilities per line of code, if you just have less code, you're going to have less.
Yeah, sure, yeah. So again, this goes to this how you can quantify whether or not a particular interface is going to protect you more than another one. And so there's a bunch of different approaches or different work that tries to offer heuristics for this. So people have done things like doing CV analyses and trying to link them to particular code paths and using that as a proxy. People have done things like complexity analyses on the different calls. People have done things like so there's a relatively recent work from NYU where they looked at popular paths through the kernel, and they said popular paths are less likely to be buggy. So all these are different kind of heuristics that we could use. For our purposes, we have, for the most part, stuck to just quantifying it and making that kind of uniform bug assumption, which
if I'm understanding you correctly, you're less actually worried about the isolation between the two entities here, and you're more worried about the ability of any entity, whether it be container, VM, process, or whatever, to actually subvert higher privileged entities below.
Right.
And then presumably once you had that, you could then use that if you so chose to
sure.
poke somebody else.
Yeah.
So okay, yeah. I'm sorry. Sorry, that was confusing.
So the presupposition is the interfaces that you do away with, when used the way they're designed, are not able to cause communication between them.
Right. Yeah. So the idea is that if we can narrow it down to a small enough set, then perhaps the right set. And what is the right set is another question as well.
So here's just a follow-up on Alex's question. So how do you evaluate what you were going to do here, given that the metric that you are trying to optimize, but doing it slightly, is also the metric that you're using to evaluate whether or not you're doing a good job? By definition, you do a great job.
Yeah. So what we try to do is the thing that we've done so far is we do this measurement, which, like you say, is kind of by design to capture the intuition, and we also try to fuzz test on it, which is also imperfect. It's not going to be
So differentially with and without those other system calls.
Yeah, that's right, and I'll show some of that in a little bit. Yeah.
Does that include, so when you have the tap interface, now you have a whole stack that you have to implement in the application, which is a vulnerability for that one application now.
Yeah.
So is that included in the metric where it's like you're
No.
kind of moving the problem?
Because that's
Yeah.
state sharing. That's your container. You can screw yourself on that.
Yeah, yeah,
So
right.
the view is that once it's you, you're kind of.
Yeah, so really, I mean, I guess to the point before, it's really the host that we're trying to protect, and if it's inside your own domain and you're not able to damage anyone else, then at least we've contained it that far. So there's some terms that people use at IBM when they talk about some of this stuff. They talk about a horizontal attack profile, which is what they would say this is, because they're really talking about which again is really like protecting the kernel. But then they talk about a vertical attack profile, which is more like what you're talking about, which is they want to be able to tell people this is your container, and we're going to try to make sure that your container stays okay. But this one is really on what they call the horizontal attack. So okay, so the approach going forward, we're going to try to whitelist the system calls, and so Linux has tools to do this, and the one that I'm going to be talking about is seccomp, which is it's a filtering system on system calls. And I should point out that people have been trying to use seccomp already on containers in order to kind of narrow this interface to the host. The thing is that it's quite difficult to do if you don't know what the domain of applications that you're trying to support on top of it are, because for you to get the properties that we're looking for, all the programs on the host must be under this fairly strict policy, or the stricter the better, really, depending on the bug density metric that you're using. And so when people have tried to put seccomp policies on their containers, they end up with very, very permissive policies. So this one has, this is the default seccomp policy. It's got about 300 calls on it, which isn't that much fewer than the number of Linux system calls. So what we do, which I guess is alluded to in the previous discussion, is to apply like some library OS techniques to these containers in order to be able to restrict that interface as much as possible. So that we're not just talking about moving the network stack now, we're talking about a full library OS. And the particular library OSs we're talking about are from the Unikernel, some of the Unikernel ecosystems that are out there. The only slight issue is that Unikernels normally run as VMs and not as processes. So, but fortunately, that's the next part of the talk. Is I'm going to describe how they can run as processes. So, so before I get into this part, I just want to go through what a unikernel is and why this is relevant for what we're trying to do. So unikernels, I think they've probably been around for, I don't know how many years, a few years, less than 5 probably. They're kind of the modern incarnation of library OS in a cloud setting. So unikernels are applications that are linked with just those library OS components that they need to be able to run directly on a virtual hardware abstraction. So basically, you can think of it as a VM that doesn't have a guest OS inside. It just has a single binary that's statically linked and running on the virtual hardware. The original unikernels were language specific, so things like Mirage OS, which is OCaml-based. Other ones like Include OS, and there's a bunch of other language ones that have come out there. And there are also these more legacy-oriented unikernels, like the rump kernel, which is based on NetBSD. So instead of focusing on a particular language for the unikernel applications, this one targets more of a POSIX-like abstraction. It's not completely POSIX, but it can surprisingly run a whole bunch of the kind of familiar cloud applications that people talk about. The things like Nginx, Redis, Node.js, Python. If I was going to try to classify what would run on RumpRun, it's mostly event loop-based things. Things that have an event loop-based flavor are the things that are going to run well on RumpRun.
As you add more of these library OS components, don't you lose out the introspection benefits that you thought you were getting by not having VMs? Because now you do have this weird piece of system stuff
Right.
you have in your address space that is not part of the standard
Right.
Unix environment.
Yeah, so that's a good point. I think there's a trade-off between that. So some of the things that you put in as the library OS, some of it is so some of it does obscure. Like if you're used to having like a system call boundary that you're looking at, you're tracing or whatever, getting stats from.
That's that.
You're right. Okay, yeah. Other things though do work even with the library OS. So things like or things that the library OS doesn't have to do because it's like a specialized version of that component. So some of the sysadmin type stuff I was talking about is no longer really done in the unikernel. It doesn't need to be done in the unikernel. But yeah, I think that's a good point. And whether or not so as I go through, like at the end, I'll talk about some of the ways that we're trying to bridge this gap. So we kind of see it as a gap. Like once you go into the library OS world, you're making certain abstractions that are convenient or familiar for containers, and you're making them more difficult. And we think there's a way to bridge a few of them together to make them more container-like and more usable while maintaining the properties that we're trying to maintain. But that's sort of like a future.
It also seems like as you go down that line,
Yeah.
you also have the opportunity to say, all right, well, maybe I don't care as much about what the underlying host OS is anymore, because I've already subsumed it by this. And a big reason you get into trouble is that the host OS, depending on if you're using Unix or Windows, was designed by people who didn't have to worry about this at all. And there were a bunch of interfaces that are really problematic. And if you got to redesign the OS with a goal of making the attack surface smaller and making it harder for people to be confused, you get rid of implicit state, you get rid of async, you do a bunch of things.
Yeah.
That would be easier to do if you weren't stuck with that thing you had.
Right. So this is also something that we've thought of quite a lot. And this is again getting into some future stuff. So basically, once we convinced ourselves that we could operate under this very limited, operate enough things under this very limited subsection of the kernel, we had these ideas that we wanted to take that little subsection and see if we could, figure out what we were using from it or what was necessary for it to be useful in this container world, and then hopefully think of something like you're talking about, like applying some type of new architectural ideas that we could do there. But for the moment, we're trying to coexist with a lot of the Kubernetes stuff and the control plane stuff that's happening on the machine, while still getting some amount of isolation out of it. Okay, so unikernels. The reason that unikernels have been sort of interesting for the past few years is that they have kind of two properties which are important for the cloud. The first one is that they're lightweight because they only contain what the application needs inside of them, and the second one is that they're isolated because they've been able to kind of ride the coattails of this VM isolation being the gold standard of isolation. And they're, as I was mentioning before, they're fairly well suited for the cloud, especially environments where the thing that you're trying to run is very special purpose, either a microservice that does one special purpose thing, or something like serverless, which focuses on a particular language, or network function virtualization, which is also very domain specific.
So when you say lightweight, what do you mean in this context when it's running the process on top of the OS underneath it?
So mostly, so say the second part of that.
So unikernels, as you said,
Yeah.
traditionally run in the VM.
Yeah. Mm-hmm.
But now you're going to have them run the process
Yeah.
on top of a regular operating system.
Yeah.
And so now it seems like it's a strict addition of layers. So
Uh,
in the kernel.
Yeah.
The application used to be able to call directly, but now I have to call the OS, which then is going to call in the kernel. Now a restricted set of the kernel granted, but it's still running on top of the whole thing.
Yeah. So what I'm talking about here is like for these unikernels that are VMs, they're lightweight when you compare them to normal VMs. They're much smaller than normal VMs. in this because they have less stuff. And so this helps with some of the distribution of the images and stuff.
So these two things are comparing against different strawmen, right? You're lightweight compared to
Yeah.
VM, and you're isolated compared to contain.
Yeah. I guess they weren't necessarily supposed to be. I guess the lightweight one is a comparison. The isolation one isn't really supposed to be a comparison. It's more like it's the reason that people have. So I think there was a trend towards having a lighter weight container for the cloud, and because the VMs were criticized for various reasons about the images being too heavy and stuff like that. And I think the one that the Unikernels sort of managed to get some ground on was that they were reducing, like you didn't have to pass around these giant images, you had these small little images. So I think that's why they managed to get some mind share. So, yeah. Yeah.
Have you looked at, like, is libc, like, the cause for this gigantic attack surface? Well, like, if I just look at libc, is that using 500 out of the 900 syscalls, or can I just fix libc instead of?
Yeah. So that's kind of an interesting question. So I guess you could take. So I don't know. The way I think about libc is it's almost like the gateway to the system calls that applications use. So it's possible that you could implement a libc that did more stuff that would make it not need to do the system calls, but that would essentially be a library operating system at that point. Does that make sense?
Yeah, but that seems easier. Then like the boundaries, like libc, and that stays the same. So when I look at it,
Right. So I mean, one way to think about what rumprun is, which is the POSIX legacy one, it really is like a libc. So you have your application, and that's your libc, which happens to have all of the NetBSD implementation behind it. So I want to say something, but I think it would be confusing. Maybe I should continue a little bit more first. Okay, so the issue. All right, let me figure out where we were. Okay, so the Unikernels, right? So I think the reason they were gaining mindshare was because of these things. However, because they were using virtualization, I think it got them. They were able to say we are isolated, but it also caused them some problems. So, for instance, the tooling for the VMs was designed for very heavyweight things. And so you wouldn't be able to get the advantages from the Unikernels that you wanted right away. And so that was pointed out by the Light VM paper, among others. The Unikernels were criticized by being difficult to debug, partially because they were in these black box VMs, which were more like debugging a kernel than debugging a process. There's deployment issues. If you already had virtualized infrastructure, it was hard to spin these things up. And other reasons. So what we did, as I said, is we decided that we were going to try to run these as processes because the Unikernels really conceptually are a single process anyway. So all we really need to do is show that we can run them as processes, and then convince ourselves that we have isolation that is equivalent or as good as that virtualization, the virtualization isolation. And if we do so, then we get a bunch of benefits, the things that come for free when you're a process. So these are things from the common tooling like TDB and perf, to memory sharing, architecture independence, ASLR, things like this. Although, to Stefan's point, some of the common tooling you still wouldn't have if you're taking the LibreOS approach. Right. So let me just jump in a little bit to how we make these run as processes. So in the normal virtualization world, when you're running a Unikernel, it runs on a virtual machine monitor. So here I have a picture of it running on QEMU. One of the early works we did was making similar observations that the Unikernel wasn't really a fully, didn't really need everything that a legacy OS would need. So we have a very lightweight specialized monitor called a Unikernel monitor. And the things that this doesn't have are things like emulating PCI, and all the stuff that you need for a legacy OS to run. And this Unikernel monitor has a very simple hypercall interface. It gives those low-level access to the network and the block devices. And yeah, stop there. Okay. So the way that this looks, I'm just going to go through what the monitor does in the normal virtualization case for Unikernels. It really the monitor has two jobs. The first one is setup and loading, and the second one is exit handling. So for setup, it first opens some file descriptors to the host. These are things for the tap device, for example, for networking, or for a block device for storage. Then it loads the Unikernel, and the way it does this is it allocates some memory that's going to tell KVM it has a Unikernel inside. It's going to load the binary into that. It's going to set up the vCPU registers and set up the page tables and things like that. And then it finally executes it tells KVM to execute the virtual CPU. While the Unikernel is running, it may do some exits, which transfer control back to the monitor, which will then perform the I/O on one of those previously opened file descriptors for the network or the disk. But like we were pointing out, Unikernels are really more like processes than kernels anyway. So, and especially because we're using this lightweight monitor here, this has shown us, it's demonstrated certain things. So I mentioned that when UKVM starts the Unikernel, it sets up the page tables for it. It actually locks down the page tables and does not allow the guest to have privilege to change them afterwards because the Unikernel doesn't need it. It's just trying to run a single application. So the Unikernels are not doing any page table manipulation. Similarly, the Unikernels are not doing anything with the interrupt handlers. While they do set up some of the interrupt descriptor tables and things like that, they're just using it for processor exceptions. They're not actually using it for any real work, any preemption or anything like that. So, and this goes to what I was saying about the ones that work are normally event loops because they all sort of use this cooperative scheduling and pull. So, because of that, the Unikernels don't actually use any of those kernel structures, so we can just run them directly as the processes and limit the system calls. So the way that we do this is it looks very similar, and so I'm just going to go through this quickly. We've changed the name of the monitor process to a tender process now because it's not really a monitor, but it has the same basic functions. It does the setup and the loading. So first it opens the file descriptors to the network device and to the tap device, so still low-level I/O access. It loads the Unikernel, but this time instead of loading it into a vCPU context and talking to KVM, it's just going to load it sort of like a dynamic library. And then, importantly, it's going to configure the seccomp filters to make sure that from now on, this process, this tender process, which has this dynamic loaded Unikernel inside of it, from now on can only make a few system calls that match the hypercalls that would have been made before. And then, of course, there's still exit handling, but it's not really exits anymore. It's just kind of function calls that use those file descriptors that were opened before on those allowed system calls. So to see why this isolation sort of matches, we note that there's a direct mapping between the hypercalls that were being done before and the system calls that were being done. So I've shown system call and resource pair because for this, we don't want to say you can have the read system call completely open. We want to say you're allowed to read to this network file descriptor, which is related to this tap interface, which was opened in the setup phase. So by doing this, we think that we have a similar or an identical interface to the host from the host perspective that was underneath the monitor as underneath the tender. So we've implemented this. It's in this. Our work is in the Solo 5 Unikernel ecosystem, and that's all on GitHub. And the prototype supports these 3 Unikernels that run in this ecosystem. So this is Mirage and IncludeOS and Runfront. So to go back to some of this measuring isolation that we use. So this is, again, if you recall, this is the code reachable through the interface. We run it in 3 different scenarios. This time the process, the UKVM unikernel, which is using virtualization, and the unikernel is a process, which we call Nabla. And this time we're running it on more realistic applications. So these are rump run applications, so Nginx, Redis, and Node, and Node Web Server. And what we're seeing, so you see a much greater change from running it as a process to running it as a virtual machine, which is the first left 2 bars. And the reason for that is because these applications are using a lot more of the kernel than our little web server was. And then the other thing is that we still have this big reduction between the virtualized case and the non-virtualized case. And again, these are the virtualization-related functions that are being called. So these are all KVM-related calls that are happening, that are being avoided, KVM-related functions. So I had mentioned before that we didn't just want to see these kind of footprints. We want to see what you could possibly access through the interface. And so to do that, we tried to apply the Trinity system call fuzzer. And so what Trinity does is it basically calls system calls with some randomized arguments to try to get coverage of the kernel. And really, it's looking to look for bugs. That's the purpose that people use it for. It's not completely random. It has these things called file descriptor providers, which sort of let you focus Trinity on particular file descriptors and that are set up in a particular way. So we modified this to add our file descriptors that we care about, so like the tap ones and the disk ones. And we ran it, I don't have the number of times we ran it here. I don't know. we ran it a bunch of times, and we plotted the system calls as a histogram. So this is just ordered based on how many function calls could be accessed through that system call by Trinity. So Trinity was able to access up to 600 and something calls for one of the system calls. That was unshare. I should have pointed out, we ran this in 3 cases. So these are all different seccomp profiles we put on it. The first one accepted everything, so that's the equivalent of just running the process with no filters. The second one is block, so that's the sort of sanity check. That's how expensive in this metric the seccomp filters are. And the third one is with our policy. And so you can see that Trinity had no trouble accessing a lot of the kernel for the process, but for ours, it did not. It was not able to access many functions. So these results are only as good as Trinity is in terms of how much of the kernel it could reach. So we also measured performance, and this is kind of what you would expect. So we are avoiding VM exits here. So when we compare against UKVM, which is our main comparison point, using virtualization, we get higher throughput, and this is mostly from avoiding the VM exits and the associated costs. So we ran this across a bunch of different benchmarks with all the different types of unikernels that we.
Sorry, before you leave that one.
Yeah.
I'm just surprised you don't have a baseline without any of that.
Without any of.
Just the process running.
Just the process running. Yeah, we don't have that baseline. So the baseline that we do have is running on QEMU, like so a normal virtual machine.
It's painfully expensive.
Yeah. So running. So yeah.
But Alex, why do you care aside from kind of pedantic reasons?
No, but the question I care is basically your libOS had to re-implement a whole bunch of stuff that was already in kernel.
Yeah.
And so the question is, do I pay for that? In other words,
is
your code roughly as fast as the kernel?
No.
Is your code
Yeah.
faster because
So
it's tighter? Is your code slower because it hasn't been machined over 20 years?
Yeah. So the answer to that is that the kernel code is faster. Sometimes it's significantly faster. So the Linux TCP stack is much faster than any of the other TCP stacks that we used. We don't have the measurements here. I think we had the measurements, but to answer your question, yes, you do pay a cost for the libOS.
So I guess this comes from my lack of, I don't know what modern QEMU KVM performance is. Back in the day, it was a dog. Maybe these days it's much better. Like, how does this look against SEN? I just don't know in terms of absolute numbers.
Okay,
Where we're
yeah.
at here. Are we 2x baseline? Are we 10x baseline? Are we?
Yeah, so there's a couple things that are playing into that. I don't have the answer. I don't have the number of X. but there's a couple things that play into it here. So one of it is the device model that's being used. So these ones, it's got this polling, and it's got a single packet in flight at a time, which is not a performance-based not a performance-based thing. So anything that is going to use high network throughput and stuff, many X, I would say, lower is what we're dealing with. The main thing that we were trying to target here, we weren't trying to argue that the library OS can be performant in terms of its network implementation or anything like that. I think there are other works that have gone in that direction. We mostly just wanted to see. I mean, really, what we wanted to see is how does it compare? Like, if we take out this virtualization, how much overhead are we taking out? I think your point is perfectly valid. We should have a baseline with the normal things. I think it would be, unfortunately, not very comparable, which is probably why we don't have it on. But yeah.
Is latency just as good or bad?
Latency?
It seems like the latency would be pretty dramatic, like with the additional network stack.
Yeah, so I think we had some experiments, but I don't have the numbers. I remember in all cases we were better. We didn't find anything where we weren't, but in terms of like which situations we were the most better. Most. Oh, okay. Yeah, let me zoom ahead a little bit. So one other thing that was kind of interesting to us was the startup time. So this is something where the Unikernels have been proposed for serverless and NFV and things like this because they have a faster startup time. And this is slightly different than that VM exit type overhead that you would expect, because this is really has to do with the startup costs. So this is like asking KVM to create the new CPU, vCPU, and things like that. And so that's what this is really showing, is that by avoiding that, you do get better performance with the running as a process, which also is not really a surprise. And for reference, this is a normal process over here. The reason that we're not as low as a normal process is because we're still doing some of this setup. We're still doing the dynamic loading of the Unikernel and things like that, which the process doesn't have to do. So just to sort of tie this back up to the containers, and I think that we touched on some of this a little bit earlier, which is how do we then make this look like a container? Because what I have described really is processes that have a thin interface to the host. I haven't described containers. And so to sort of do this, we needed to understand what exactly a container was and what was important to the containers. And this had to do, has to do with what the container's relationship is to host hosted abstractions like file systems, et cetera. So as a first step, we just kind of threw this into a container. We just kind of wedged it in. And we made a new runtime called run-nc. And we hid all the libOS details as much as possible from people. So we gave sample containers and base images that they could build from, so they didn't have to go through the libOS building steps. And this was open sourced, and it got a bit of buzz, which was a little bit uncomfortable because all the buzz very much oversold everything. But I think it indicated to us that it is something that the industry cares about, this problem. So some of the things that we're looking at have to do with how to understand whether or not this minimal or this small component this small piece of the kernel, how to improve that metric, or how to have better guarantees that this metric is, or that this piece of code underneath, that we're restricting to the right system calls. These are the system calls that we should be restricting it to, things like this. We're also looking at, like I said, things that make this feel a lot more like a container. And one of the main things we're looking at there is the file system, because file systems are really quite fundamental to how containers start up. But I think I'm just going to stop there. Yeah, and just to summarize, so we're looking at this container isolation space. We've tried to make the claim that virtualization hardware mechanisms are not needed for isolation, and and our approach is to limit the system call interface, and then try to adapt this into the container ecosystem. So yeah, that's it. Yeah.
So, I guess if you're worried about a co-located container owning you, that's one thing. But if you're pulling in this new network stack that will talk to the internet,
Yeah.
and this network stack is presumably, is there a reason to believe that it's less buggy than the Linux network stack? So can that just get into the front door?
Well, so, okay, so if you are using a network stack that is more buggy than the Linux, this is what you're saying, right? If you, in the library OS, you have one that has more bugs, then you have just opened yourself up to more direct attacks. Is that what you're saying? Yeah, I mean, I think that's a concern. Although so that's a concern that we would say is in the horizontal attack profile space. So that's something that we would want to address at some point, but that would be preferable than the whole host to us. Preferable than the whole host getting. So it's almost like it's the problem of the container to deal with, which ultimately we want to help with, but.
But you just made that problem harder, right? Maybe.
Maybe, yeah. Yeah, well, yeah, so in that area, there's also things that we are interested in looking at that have to do with splitting that piece up into multiple components.
Maybe another way of constructing it is a fairer way to do your metric, where you're looking at the reachability of code.
Yeah.
Would be to include the libOS code in your address space, because that is network accessible. Because in fact, that represents the entirety of the attack surface for a given container, the stuff that can be accessed via both the underlying host, but also, so you may have this very thin waist of your interface at the syscall level, but then you accept packets that have like a method number as their first argument, and it just explodes this whole set of things you can invoke.
Yeah. Yeah, I mean, so one of the things we've been thinking about is whether or not there should be a single address space that this thing that includes the library OS should live in. So right now, yeah, we're putting the library OS in with the application, and that means that we're increasing the attack surface to that. If we put the library OS in with some protection from the application, which I know is not exactly like a library OS thing, then we could start to do some separation of concerns there. And so this is something that we're interested in looking at, but I don't have a very, very good answer for it. But I understand the point. Thank you. All right.